Welcome back, ladies and gents. In this teaching video, I'll be looking at part 4 of 7.4 static of rigid bodies. So we will be studying two types of problems, pegs and strings. Now, when a rigid body is in equilibrium, two conditions are satisfied. Number one, the sum of clockwise moment is equal to the sum of anti-clockwise moment. Number two, the resultant force horizontally or vertically is zero. To calculate the moment of a force, we have to use the formula force multiplied by the perpendicular distance. Now, for simplicity, we'll be considering the horizontal and vertical forces only. Here is exam style question 1. A uniform rod AB has length 4 meter and weight 160 newtons. The rod rests against a fixed smooth peg at the point C, where the distance A to C is equal to 3 meters. And the end A of the rod rests on rough horizontal ground. So on this horizontal ground, we will have friction. Given that cos theta is equal to 3/4 and the rod is in a limiting equilibrium, part A, show that the magnitude of the force acting on the rod at C is 80 newtons, and part B, find the coefficient of friction between the rod and the ground. So ladies and gents, I'm going to start by labeling all the distances and forces acting on this particular uniform rod. Because it's a uniform rod, the weight 160 newtons will act at the center. This will split the distance 4 meters into two equal parts, so 4 divided by 2 is 2. So this part over here is 2 meters. The distance A to C is equal to 3 meter, so 3 take away 2 is 1 meter. So that portion is 1 meter. Now the distance A to B is 4 meters. 4 take away 3 gives us 1 meter. So this distance over here, C to B, is 1 meter. Now, because the uniform rod is in contact with the smooth peg, there will be a normal reaction coming out at the point C. Okay, so here is my normal reaction. It is perpendicular to the uniform rod. Now for this normal reaction, we will have component forces. The horizontal and vertical component, we can construct a right angle triangle. So here's my right angle triangle. So I can put in the arrows. Now it can be shown that this particular angle is precisely theta. This is the adjacent, so it will be RC cos theta. This is the opposite, so it will be RC sine theta. Now the uniform rod is in contact with the rough horizontal ground. So at the point A, we will have a normal reaction coming out, which is perpendicular to the contact surface. Now, this rod is in limiting equilibrium, so it's about to move. If it was about to move, it's going to move to the left. And so if it moves to the left, friction has to act to the right. So that friction will be acting to the right. Because the uniform rod is in limiting equilibrium, friction has reached its maximum. So we can label this as our maximum friction, which is given by mu multiplied by the normal reaction at the point A. So we can label it as mu RA. So that there completes the diagram. I've got my distances and I've got my forces. Right, so in part A, we want to show that the magnitude of the force acting on the rod at C is 80 newtons. So we are trying to show that RC is equal to 80 newtons. So let's have a look at part A. Our target is to show that RC is equal to 80 newtons. Two conditions are satisfied when a body is in equilibrium. Number one, the sum of clockwise moment is equal to the sum of anti-clockwise moment. Number two, resultant force horizontally or vertically is zero. Now, if I go back to my diagram, I've got 1, 2, 3. 3 unknowns. So I want to eliminate the RA and the mu. To do this, I can take moments about A. If I take moments about A, all the forces coming out of A are now neglected. So let's take moments about A to calculate RC. So we know that the sum of clockwise moment is equal to the sum of anti-clockwise moment. If I put my pen at the point A, ladies and gents, I know that the 160 newtons is going to take the uniform rod clockwise and the RC will take the uniform rod anti-clockwise. Let's start off with the clockwise moment. So we can form a diagram. I've got my 160 newtons I can sort of stretch it downwards, okay, form a right angle triangle. Okay, now the distance from the point A to that weight is 2 meters, so I can label 2 over here. What is my perpendicular distance to the force 160? Well, the perpendicular distance is this component over here, which is the adjacent. It will be 2 cos theta. Equal. Now, let's have a look at the anti-clockwise moment, the RC force. Now, here's my RC force. I'm going to draw a diagram. The distance from A to RC, which is perpendicular, is technically the 3 meters. Okay, so we have 3 meters here. Now we're going to calculate the moments of each of these forces. Let's start off with the 160 newtons. So we've got 160 multiplied by the perpendicular distance 2 cos theta. This must equal to the moment of the RC force, which is 3 times RC. Right, we've got cos theta, which is 3 over 4. So I can substitute cos theta, which is 3 over 4, equal to 3RC. Right, now we can clean this up. So if I clean this up, I get 240 is equal to 3RC. Hence, RC is equal to 240 divided by 3, which is precisely 80 newtons as required. So that there completes part A. Let's have a look at part B. Find the coefficient of friction between the rod and the ground. Now, that mu is acting in the horizontal direction. So I'm going to resolve horizontally, taking right to be the positive direction. We know that the resultant force horizontally is equal to 0. So what is that resultant force horizontally? Well, it will just be mu RA. Okay, so mu RA minus RC sine theta. So that resultant force has to equal 0. Now we can make mu the subject. So if I make mu the subject, I get mu equal to RC sine theta divided by RA. But I know what RC is equal to. It is 80 newtons. I can also calculate the exact value of sine theta. Using the information, cos theta is equal to 3 over 4. So I need to construct a right angle triangle. So 3 over 4 represents adjacent of a hypotenuse. So the adjacent is 3 and the hypotenuse is 4. We can use Pythagoras theorem to work out the opposite, and that will just be square root 7. So from this diagram, sine theta is equal to opposite over hypotenuse. So that will be square root 7 over 4. So we've got the exact value of sine theta. We also know what RC is. That is 80 newtons. So we can substitute that in to give us mu equal 80 multiplied by the exact value of sine theta, which is square root 7 over 4. We divide this by RA. Okay, so we're nearly there. To calculate mu, we also now need to calculate RA. So if we look at RA, it's acting in the vertical direction. So now I'm going to resolve vertically, taking upwards to be the positive direction. The resultant force vertically is equal to 0. So what is that resultant force vertically? Well, it will just be RA plus RC cos theta minus 160. Okay, so that's my resultant force vertically. This is equal to 0. So now I can make RA the subject. RA is equal to 160 minus RC cos theta. Okay, so that there is RA. Now we know what RC is. That is 80 newtons, and cos theta is 3 over 4. So we can substitute this in. We've got RA is equal to 160 minus 80 multiplied by cos theta, which is 3 over 4. I can now put this into my calculator, and if I do this, I get RA equal to 100. Okay, so now I've got my RA, I can substitute that into here to work out my mu. So mu, the coefficient of friction, is equal to 80 multiplied by square root 7 over 4, all divided by 100. Okay, so now I can put this into my calculator. If I put this into my calculator, I get mu equal square root 7 over 5. So that there is the coefficient of friction between the rod and the ground. So essentially for part B, I've used condition number 2. Resultant force horizontally or vertically is 0. I resolved horizontally, resolved vertically, and at the end I got my value for the coefficient of friction. Here is exam style question 2. A uniform rod AB of mass 6 kg and length 1.6 meter rests with its end A on rough horizontal ground. So on the horizontal ground over here at the point A, we will have friction. The rod is held in equilibrium by a light string attached to the rod at B. The tension in the string is T newtons. The coefficient of friction between the ground and the rod is mu. Part A, show that T is equal to 27.1 newtons to 3 significant figures. And part B, find the range of possible values of mu for which equilibrium is possible. So I'm going to start by labeling all the distances and forces acting on this particular uniform rod. We have the weight acting at the center, so that weight will be 6g, where g is equal to 9.8. This weight is going to split the distance 1.6 meters into 2 equal parts. So 1.6 divided by 2 is 0.8. So we have 0.8 from here to here, and we have 0.8 from here to here. Okay, now let's look at the point A. The uniform rod is in contact with the horizontal ground, so at the point A we will have normal reaction coming out. So that normal reaction, we can call it RA. It is perpendicular to the contact surface. Now, this particular uniform rod, if it was to slip, it will slip to the left, and so friction will act to the right. So we can label the friction at the point A acting to the right, and we can call it FA. Now, this tension force over here is acting at an angle of 40 degrees to this particular horizontal. So it will have component forces. We can form a right angle triangle. So we can put the arrow to the left and the arrow going up. Now this component over here represents the adjacent. It will just be T cos 40 degrees. And this component over here represents the opposite. It will be T sine 40 degrees. This angle over here is going to equal 30 degrees. Alternate angles are equal. That there's my complete force diagram. So I've labeled the forces and the distances. Now in part A, we want to show that T is equal to 27.1 newtons. So let's have a look at part A. We know that two conditions are satisfied. Here is the first one, here is the second one. So which one of these two conditions am I going to use in order to work out T? So over here we have RA and FA, two unknowns, and over here we have T, another unknown. To eliminate the RA and FA, I can take moments about the point A. That will leave me with one unknown, which is the T. So to work out T, we're going to take moments about the point A. So moments about A. We know that the sum of clockwise moment is equal to the sum of anti-clockwise moment. So sum of clockwise moment is equal to the sum of anti-clockwise moment. So if I take moments about the point A, the 6g weight will take the whole body clockwise, and the T newtons will take the whole body anti-clockwise. Let's start off with the 6g. We can form a diagram. So here is 6g. I can stretch the weight 6g. So now we can construct a right angle triangle. This particular angle is going to be 30 degrees. Now the distance from the point A to the weight is going to be 0.8, so we can label 0.8 over here. The perpendicular distance to my force 6G is going to be this component, which is the adjacent. So that will be 0.8 cos 30 degrees equal. Now we're going to look at the anti-clockwise moment, the T newtons. Right, this one is very interesting. So we've got this distance, which is 1.6. And we know that this combined angle is 70 degrees. This distance 1.6 is not perpendicular to the tension force. But if I construct a right angle triangle, drop a perpendicular like this, I see that this component of this triangle is going to be perpendicular to the tension force. So what will that component be? Well, it represents the opposite. So it will just be 1.6 sine 70 degrees. Okay, so now we're going to calculate the moment of the 6G and the T force. Let's start off with the 6G force. So we have 6G multiplied by the perpendicular distance, 0.8 cos 30 degrees. Okay. This must equal the tension multiplied by the perpendicular distance to that tension force, which is 1.6 sine 70 degrees. Okay, so I can simplify this. And if I do this, I get 4.8 G cos 30 degrees is equal to 1.6 T sine 70 degrees. Now I can make T the subject. So T is equal to 4.8 G cos 30 degrees divided by 1.6 sine 70 degrees. I can put this into my calculator, making sure my calculator is in degree mode. And if I do this, I end up with T equal to 27.1 newtons to 3 significant figures. That completes part A. Now in part B, it says find the range of possible values of U for which equilibrium is possible. So my answer will be in inequality form, because of the word range. So let's have a look at part B. Now equilibrium implies that the friction force Fa at the point A has to be less than or equal to the maximum friction at the point A. So F max. So this implies that Fa is less than or equal to mu multiplied by the normal reaction at the point A. So our target now is to work out Fa and Ra. If we can work out these two forces, we can then rearrange and work out the range of possible values of mu. Let's look at Fa. It's acting in the horizontal direction. So I'm going to use condition number 2. Resolve horizontally, taking right to be the positive direction. We know that the resultant force horizontally is going to equal 0. So what is that resultant force? Well, it will be Fa minus T cos 40 equal to 0. We can rearrange and we get Fa is equal to T cos 40. But we know what T is. This is T in exact form. So I'm going to substitute T. Fa is equal 4.8 G cos 30 degrees divided by 1.6 sine 70 degrees. Okay, multiplied by cos 40 degrees. So I can substitute G equal 9.8 and this whole thing into my calculator. If I do this, I get Fa equal to 20.8 in newtons to 3 significant figures. Now I'm going to work out RA, the normal reaction at the point A. RA is acting in the vertical direction. So we can resolve vertically, taking upwards to be the positive direction, and we know that the resultant force vertically is going to equal 0. Okay, so we have RA plus T sine 40 minus 6G. This must equal to 0. Rearranging this gives us RA is equal to 6G minus T sine 40. We know G is equal to 9.8, and we know the exact value of T, which is this one here. So substituting T gives me RA equal to 6G minus 4.8 G cos 30 divided by 1.6 sine 70. This whole thing multiplied by sine 40. We can put this whole thing into our calculator with G equal to 9.8, and if we do this we get RA is equal to 41.4 newtons to 3 significant figures. We've got our FA and we've got RA. We're going to substitute these two into this particular inequality. So we've got 20.8 is less than or equal to 41.4 mu. We can write it the other way around. So 41.4 mu has to therefore be greater than or equal to 20.8. Making mu the subject gives us mu is greater than or equal to 20.8 divided by 41.4. To 3 significant figures, this will be 0.502. Hence, the range of possible values of mu for which equilibrium is possible is mu is greater than or equal to 0.502. Okay, so that there completes part B of the question and this exam style question. Now, like always, if you found this video useful, please don't forget to leave a comment, leave a like, subscribe to my channel, turn on the notification bell so that whenever I post teaching videos, you have a notification and you can start watching the teaching video.